Hello everyone, welcome back to the summer school on galaxy and cosmology. I hope you have refreshed and recharged yourself and you're ready for this lecture. For you who have just joined the school, my name is Luki Puspitarini from Institut Teknologi Bandung, and you can call me Luki. Now we will continue this session with Dr. Muhammad Ikbal Arifyanto. So Dr. Muhammad Ikbal Arifyanto will explain more about Milky Way and local group. Before starting, let me inform you again about the participant etiquette. So please don't forget to rename your username as instructed before. Please mute your microphone and turn off your video unless the moderator allows you. And please give your full attention to the lecture. And if you have question, you can type your question in chat or you can raise your hand. Okay, now, so please welcome Dr. Muhammad Ikbal Arifyanto.
Okay, thank you. This is Milky Puspitarini. Yeah, in this second sessions, I will explain about the galactic halo, about the outer part of the Milky Way, but the most how is it, violence, because there are many interaction with the satellites, and nowadays after Gaia we have recent major merger with sometimes they call it Enceladus galaxy, dwarf galaxy, or the other groups say it's a Gaia sausage, because we saw it's like a distribution like a sausage or Wurst or German Wurst, or like that. But the problem is that our environment, galaxy environment, is violent, because from our point of view, cold dark matter paradigm, we that around our galaxy there are many small galaxies, and merger is still ongoing. So we will see, and also we will talk about how to determine the dark matter in the using the rotation curve, and also using local dark matter using stellar tracers. Okay, I will share my screen. So, okay, can you see the slides? Yes. Hope. Luki, lihat. Can you see the slides?
Yes. Yes, sir.
Yes,
Okay.
we can see clearly.
Yeah. Okay. Yeah. Now it's about Milky Way and local group, about dark matter and formations of the galaxy. First, we'll talk about the dark matter. How can we measure the dark matter? We can measure the local measure. Local means around the sun distribution in the disk, and galactic disk, and the global measures of galaxies using the rotation curve from the galaxy. Okay. If there's a noise here. Okay. Excuse me, can anyone mute all the participants? Okay, I will to measure the global. I will talk about the how to measure with the global measures first in around galaxy, because it's our basics. If we measure before we measure the rotation curve of our galaxy using hydrogen neutral or stars, and we can see if there's any contributions, difference between the dark matter or luminous matter, or like baryon, like stars or gas, and compare with the assumed halo or corona population. Okay, here we can see here the rotation curve with, from different galaxies, and most of them has a flat rotation curve outside around until 20 kiloparsec from the center. Here we can also measure the contribution of dark matter. Here, if this is for example rotation curve of the galaxy, our galaxy, this is a position of our sun here. From distribution of bulbs, and this the sun should be here about 160 kilometers per second, but the measurement around the sun's rotation curve around the sun, the velocity is around 220 kilometers per second, and also reaching until about 30 kiloparsecs. So contribution from the bulbs and this, and also gas or visible matter will down here back to like because the density or the number of stars beyond the 20 kiloparsec is becomes smaller, and also the contribution is also smaller for the mass, visible mass. So the difference here, so we fit with the assumed spherical distributions as a dark matter halo. Here, like this is a, or we call it also corona. This is contribution of this spheroid and this from star in this and bulbs, and this is a spherical dark matter halo or corona. So we can make this function flat. Now we want to talk about how we the problem is how we make how we know how can we know the distribution of these bulbs from our observation, and then we assume distribution of the dark halo. First, we have to see the potential of the Milky Way. Remember, in this morning, I talked about the distribution of bulbs, thin disk, thick disk, and now we will talk about the halo. But first, for the thin disk and thick disk, for the bulbs, we make a potential, like a spherical potential. You can make assume plot it like this. For this, this is our potential. We call the Miyamoto Nagai, and the bulbs is the Helmholtz potentials. So, and also for halo, we using NFW, Navarro, Frank, and White potential. Yeah, we can fit with other type of potential. Yes, this is from the Irgang et al. 2013 distribution. The mass of bulbs is about 9 to 10 to power of 9 solar mass, with scale length about 0.2 kiloparsecs. The disk is the mass, stellar disk is 6.6 10 power of 10 solar mass, and the halo is 10 to 12 solar mass. It's a virial mass of very big compared to the disk and mass. It's about 1/100 fractions. This is if we plot the potential and change to the what we call in the stellar dynamics, we call it a relation between the potential to density relation. So we can plot the distribution, the density distribution of our bulbs. This is a spherical bulbs, and this is from our this Miyamoto Nagai disc. This is a combinations with spherical near spherical center and axis symmetric disc in near suns until radius large radius, and this is potential of density of our dark halo. If we combine these three, we have the 3D distribution, density distribution of our galaxy. From how do we know this? We know from the observation of star in different directions, observation to the galactic belts, and also from the stellar halo. So, okay. So who the first one who first measure the rotation curve? It's the famous one is Vera Rubin. She measured the stars rotating in the extra galaxies, and stars are moving faster than expected. Yeah. So after we know the potential, we want to plot the surface brightness and also the mass distributions and also the velocity distributions of the exponential disk. This is what we call it the exponential disk from the here surface density, and we can integrate it with our knowledge, integrate a simple integral with the mass distributions, and this is velocity. This is I and K is a modified Bessel functions. To fit with the observed rotation curve, you can also maximize the contribution of this. For example, if SA type galaxy like SA or SB dominate with the bulbs and this, so we can maximize this contribution of this. And also we have density of the bulbs. This is volume density, and this is the mass and the rotation. It's maximum with Atlas is the maximum radius we integrate with the bulbs contribute all, and this is the called halo. Maybe is isothermal halo, which is from mass and velocity. From this parameters and functions, we can fit the rotation curve using this relations. This is contribution of halo. This is actually a mass. Mass is equals to rotation velocity square divided by radius. So this is contribution of halo. This is from gas, and this is from this on bulbs. It should be. And the contribution of halo is there are some type. This is a NFW halo, and this is isothermal halo, and also okay, with different parameter. Just but NFV parameter is large in this, then this is with the core, the halo dark matter with core in the central, and NFW is the densities become higher in the distant close to zero or unlimited. Yes, this is the rotation curve for the previous galaxy. We will fit this contribution from halo and this. We can compare this to provide luminous mass in the galaxy and compare with the dark mass of the galaxy. Yeah, from our knowledge with the galactic potential, we can measure also the orbits of stars in the galaxy. This is a stellar orbit in the Milky Way. Okay, let me stop first and share this screen. So we know the potential. This is the galactic potentials. And to know the potential, if we want to know the force or K, it's gradient potential with a distance like this. If we know the potential, we can measure the force here. From the force, we can measure this is from the positions and velocity. So we can check from the force, we can check the orbit. This is x0, v0, xi. This is we can determine the orbit of star. And the potential is from bulbs, this, and halo. So let me back. Sorry. Okay. Yes. So the orbit, it will be determined with the initial value. Initial value is star positions and the velocity. So we have to measure the distance, proper motion, and radial velocity. It also relates with the population of the star. If the star belongs to the thin disk population, so the orbit will be here, a circle, and also like this. The scale, this is x and y, and this is r, x square to y square, square root, and this is a z direction in the above the galactic plane. So the orbit will be they remember with this orbit they circling galactic center and also going up and down in the so in up and down for the thin disk population. The maximum will be maybe around 100 or few maximum is about can be reached a few hundred parsecs around near the around the galactic center. It's like just like that. If the stars belong to the thick disk, so we can go higher to the Z distribution, so like this. This is and if the stars belong to the halo, for example, so there is orbit like there, and it can reach the until 1 kiloparsecs above the galactic plane. 2 kiloparsecs belong to the halo. So we can actually this the force we can integrate to find the position. So we can select the stars and divide the star which belong to the thin disk, thick disk, or the halo by using their orbit. From the orbit also we have also the energy, angular momentum, and also we also measure the action and angle. So we want to find some integral of motion, the constant. So when star or mix in the sample, we have a sample of stars, and we can determine which stars belong to the population. Also, we can also determine which stars belong to the merger galactic dwarf galaxy. So we can measure the stellar streams. We call it streams from the satellite galaxies. So this is an example to usual if we know the potentials of the distribution like bulbs, disk, and halo, and we can measure the rotation curve and determine the contribution of the baryonic mass. And from the potential, we can also determine the stellar orbit on the Milky Way, and we can determine if the stars belong to the thin disk, thick disk, halo, or belongs to the satellite galaxy outside the Milky Way who merge into the galactic disk. Now we want to measure the local dark matter. So first, what is local? Local, it depends on your data. If you have a complete sample of only maybe 10 parsec, so you have a complete volume limited sample. But you can, if you select only from certain stellar spectra like A star or F or giant star, so you can your local is maybe a few hundred parsec away. Depends on your distributions of stars. Now, from our knowledge of rotation curve, we can find distribution from the potential of the dark matter halo. So we can extrapolate it. If this is a position of the sun, how large is a dark matter density here in the, because the idea to measure this local dark matter density is we want to detect the dark matter using our knowledge of particle physics or other maybe you will hear in the next few days about the direct detections of dark matter using our knowledge of particle physics like winds or other exotic particles. So we have to know first how many dark matter are inside solar neighborhood. So first we want to measure for the local one, we want to measure this area from the local sample. We have to find the stellar tracers. We don't observe all stars in the same, but we can observe find data from position and velocity of certain stars as our tracer. This is density of dark matter from recent measurements. Now this is from Xia et al. In 2016, and the measurements is around 0.015 solar mass per parsec cubic. This and total mass density around the sun of matter and star and dark matter is about 0.09. So its contribution of dark matter is quite small in the solar neighborhood, but it's still important quantity. So what happened if what's halo shapes of our dark matter? If our dark matter is local, is bigger than the global, it's a oblate spheroid. But it's dark matter local than the global, it's a prolate spheroid. It's like a distributions of our dark matter halo. Now, to measure and to calculate the dark matter density, we need our basic knowledge about the stellar dynamic or galactic dynamic. First, we have this Boltzmann, or we call another one, class of equations. Here is what we call it. It's Boltzmann equations. If there's no any the assumption, sorry, if the steady state assumptions, so it will this part is should be zero. Like if no steady state, if there are any merger, so this part is not zero. Now we will talk about this, about relation between the velocity. This is F is phase space coordinate. This is positions and velocity. R is positions, phi is potentials, and P is the velocity. So we want to know the distribution of star with certain in the position x, y, z, and position and velocity v, velocity px, py, and pz, pz. From Boltzmann equation, we can derive with assume axisymmetric drift, axisymmetric coordinate, Jeans equation. This is first order moment equation. So Jeans equation is equations. Uh, from this, we have to assume some statement. Yeah. First, the system is in steady state. If our galaxy survive about more than 10 billion years and no any merger, so we can call it our galaxy in steady state. So there's still star formation, then also there's star. So star come in and star out is the same, like or we can call it with steady state, no other contribution from outside. But the problem is still from our knowledge and later in the halo that our galaxy was still accreting the small galaxy. So these assumptions could be uh, uh, wrong also. But in this session, people in this measurement, we can say it's still right in some certain condition. And also the gravitational potential in the Milky Way is axis symmetric. The tilt term is ignored initially for simplicity. The tilt term is here, this contribution between R, Z, and this is R is in the galactic disk, Z the rotation, and also the phi contribution phi is if axis symmetric is 0, is constant. It's an angle, azimuthal angle. And also the rotation curve is flat with both R and Z in the solar neighborhood, so we can measure it's also one part of this become 0, and the total mass density consists of star, gas, and dark matter. If we measure the density, it should be belong to the total dynamic mass. So we have this Jeans equations from this is KZ, this is force, a vertical force. This is from radial force. This is a tilt term between relation between R and Z, dispersion. Sigma is velocity dispersion. Nu is density. And this part is the axial term. So we can assume this part is 0 if no relation at all with other with R and Z or phi and Z. We have also another equation. We call it a Poisson equation. This is a gravitational potential and mass density relation. We have potentials. We can determine the total mass density. Total mass density belongs to the baryonic mass and also dark matter mass. We can expand in cylindrical coordinate into these relations. You can see this is actually the gradient of the force in the Z direction. Using axisymmetric assumptions, we can solve this is axisymmetric, it becomes 0. The Poisson equations become like this, and we can solve this using our assumption with flat rotation curve. Since we can find odd constants A and B, this is with other measurements. So then we have two equations. This from the Boltzmann equation. We have the force in Z, 1 over density and differential from Z direction, density and velocity dispersions. Let me in 1932 and also in 1960, I think, Jan Oort, a Dutch astronomer, first measure this force and calculate this total mass density, and then he compared with the density from star population and gas population, and he found that there is discrepancies. He call it as a missing mass problem, because the total mass density is larger than the total light density from star and gas. So this is a year early from paper of Zwicky from measurement of the coma clusters. Okay, I will explain what Jan Oort already measures. Here I have I write Z is equal 1 over, this is a density, Z times, and also our knowledge of Poisson equation is total. It's also the force is also total from baryonic and dark matter. So we can use this here is we know that the force is gradient of is Z is potential, so it's actually 4P rho. So if we know the gradient of the force, we can measure the total density. Now, how to measure the force? We need to information about this number density, stellar number density, and dispersion velocity. Dispersion velocity. If we integrate, you can K is about 2 pi G rho time Z, like that. It's like so it's actually a surface mass density. We call it in it surface mass density. So from this data, or have measured the force, the Kz. So the Kz plot is Z. Is Z. It's or it's like this. This is near, say it's 50, 100, 150 parsecs around the sun. So actually, from this, Oort measure the gradient. The gradient is big Z and dz. It's equal to rho total. So from this gradient, we can calculate the total mass density of the, and then compare with the baryon mass. It's stars and gas, interstellar. This is the first method Oort has did in 1932, and he also measure it again with the new data on stellar position velocity in 1960. Okay, let me back again and share the yeah. From this we can measure the density. So first we need to know the stellar tracers. The tracer, we should measure the surface density or volume number density here. And plot usually for this stars, it's relation is exponential this, and also measure the velocity dispersion with related to the distance above the galactic plane. And this is the surface brightness. Its surface brightness is related to the k or force in the z direction. So if you know the gradient, so you can measure the total mass density. So the problem is we need a good tracer. Why we need a good tracer? Because uh, uh, the star as a tracer is already mixed with the potential of this on galaxy or galaxy mix. So the star should be old enough, traveling merge with the potential of the galaxy. You cannot use like OB stars because it's very young. It's still related to the density of the interstellar medium in the star forming region. So, and it's still with the gas, so it's still you cannot say it's already mixed sample. So you need stars already old enough, or you can also well populate in good statistic at high z direction. So you need the stars is bright enough with bright absolute magnitude, so you can see until z a few kiloparsec maybe, or a few hundred parsecs. And volume complete, so you need to in one volume. This is helpful if, for example, few hundred 500 parsec, you need to all the stellar sample it's complete, so you don't find any missing stars, or you cannot detect stars because your, or for example, limited survey or something like that. So you need a deep survey to find a star with certain magnitude. So you can usually use a giant red giant branch stars because it's bright enough until very high distance. And also you need to measure velocity data. The problem is before Gaia is we lack of measurement of radial velocity and also the proper motions. So the velocity is a problem. But now in the Gaia era, we have many stars with 3D velocity and also good distance with a good parallax. Here, the dark matter density from right in 2014. Here, most of recent measurement, this is using Hipparcos measurement using SDSS, RAVE, and also this is from Gaia, and from Gaia launch. It is in 2014 before the launch of Gaia. So the density is around 0.01 solar mass per parsec cubic. You see this what's pointing out that in Captain in the early in the 1920 measure with a different proportion mentioned that the density he thought that there's like a dark matter because we compare with the mass or other density of distribution of stars, and you cannot see. But I don't think that Captain thought about the dark matter is the same as what we us thought about the dark matter. Yeah, okay. I changed to the galactic halo. This is our recent measurements about dark matter density, mass density around 0.01. It's important for us to detect direct detection of dark matter. Yeah, then we have in the halo, larger part of our Milky Way is we have about 150 known globular cluster. Most of them are within the 42 kiloparsec around the galactic center, and the other furthest until 123 kiloparsecs. From this 150, we separated the globular cluster belongs to the halo globular cluster, and also there's a disk globular cluster. It's because it's closer to the galactic disk, and this globular cluster has a higher metallicity. The age range from 11 to 13 gigayear, and luminous halo star found until 50 kiloparsecs. You have a mass to light ratio is equal to 1, so most of them almost no dark matter. In the galactic halo, we have also contains field star and globular cluster. Field star have a high velocity component perpendicular to the plane, and two population, as I said earlier, globular cluster, they have metal poor globular cluster with from spherical halo distribution in near the halo, and also there are metal rich globular cluster. It's a younger and closer to the galactic disk. Exception is 47 Tuk. That is below the galactic plane and high metallicity. It's really belong to the halo, or there's a process we don't know why there are very large metallicity from 47 to. And there are also distant one, maybe Kepler strip dwarf galaxy like the Omega Centauri or Sagittarius dwarf galaxy. Our halo is from number density, it's a spherical distribution. It's a power law here. This is the density from galactic center, normalized, and power is between -3 and -3.5. Okay, the density is very small. This is about 0.2 percent from the thin disk density. So if we have about 100 or 1,000, maybe 1,000 star in the galactic disk and near the sun, so maybe we have only maximum two stars belong to the halo in the galactic disk. It's very small. But if we measure the star above the galactic plane higher, so there are many halo stars in that high. Halo can also describe the R 1/4 law in the visible, like de Vogler law. Yes, this this and halo component from the stellar halo. This recent measurement from Carolo et al. In 2007 and also in 2010, there's that our halo. This is a relation between the disk. This is a z velocity up, and then the halo is a constant velocity. Also from this is metal rich and this is metal poor. This is metal rich, z and rotational velocity. It is a d stars, and the halo star rotation is almost constant with very high velocity dispersion, like this. This is top left, the star show clear rotation velocity lag, and this is bottom this no, and then bottom right halo velocity displacement increase consistent with being to the photometric error, but usually it's a constant. And from the velocity distributions of the halo, this and halo, this is belong to the this is z direction, a distance from 0.8 to 1.2 kiloparsec above the plane in the north galactic pole. This is from 1.5 to 2 kiloparsec. This is from 2 to 3. This is 5 to 7. See, from this is dominated by the near zero. I mean the velocity of the sun. It is dominated by this. This is thin disk, and this one is thick disk, and this one's small and it's a halo. If we going higher, so the contribution of halo population and thick disk become higher, and contribution from thin disk become lower, smaller. From 2 to 3 kiloparsec, the halo dominates, and from 5 to 7, you can say there's no contribution of the disk star anymore. This is a pure halo in about velocity about 200 kilometers per second. If you assume that the solar it's equal to 0, so it's actually at if you add 200 negative velocity. If you assume that our sun is velocity, rotation velocity is to about 220 kilometers per second. So the halo is unimodal Gaussian velocity distribution, in only one distribution. This is from metallicity. We can see that this is the metallicity of the disk or thick disk, and this is the metallicity of halo. This one is kinematics. It's quite constant here, but the disk has a relation of decreasing velocity. This is thick disk and halo. Now, Carollo et al. In 2007 and 2010 has found that the stellar halo has two subcomponents. They call it inner halo here, and also there's also outer halo. If we compare the distribution, the inner halo here stop until Z max about 10 until 20, and then flat. But the outer halo is still decreasing velocity with the very low metallicity, less than -2 metallicity, and flat in Z larger than 20 kiloparsec. And the assembly process, how our stellar halo has a two, this is like a prograde rotation, and this is a retrograde rotation. This is assembly process is at work. Maybe monolithic collapse is unlikely. We cannot, I will discuss monolithic collapse, that the formation of the galaxy collapse, but because it's two directions, maybe it's because of the merger from the outer galaxy with with the retrograde orbit. This is a density map from SDSS and CGU data about the dual halo. This is the inner halo, and the bluer part is the outer halo. Now, because there's two stellar halo, and also there are also the dark matter halo, so people think, so what? How is the formations of the galaxy related to how formation of the halo is related? First, in 1962, three astronomers, Egan, Lindenbell, and Sandage, submitted a paper with title "Evidence from the Motions of All Stars that the Galaxy Collapsed." He measures the dynamics and metallicity of just only 100 stars in the halo, and they built an excellent case to find that. And he found that the 10 gigayears ago, the galaxy formed from the collapse of a cloud of gas, like the formation of a solar system from the single cloud collapse and rotates and then become a disk, and there's planet. But now it's the giant cloud collapse and rotates, and the radial collapse was halted by rotations, and the rotation here already formed stars in the halo formed first, and then uh, after the gas was rotate, it become formation of the galactic disk. This is the radial collapse, and formation of the halo was very rapid in before formation of the galactic disk. The older stars and globular cluster that we find the halo have formed at this time in initial collapse and as evident by their highly eccentric orbits. Younger stars in the disk have formed later, as evident by circular. So from this about 100 data, they found a very high eccentric orbit of halo population and compare with the disk population, and assumes that the monolithic collapse is the formation of the galaxy. But the problem is that we found first the globular cluster. We have two separate subpopulation of the globular cluster. First with the low metallicity and with the high metallicity. The high metallicity is closer to the galactic disk, and the low metallicity closer to the dark halo. And we found also the streams, what we call the halo streams. Streams is like patch of star. This is right ascensions, and this is declination, the direction. So we, with the technique Below-Kurov and team, using SDSS data, found there's Sagittarius streams here, and also Virgo overdensity, orphan stream, and monoceros stream using F star, red giant branch stars, and density star, and plot in the halo how they call it as a tidal stream. Not all stars are smoothly distributed throughout the halo, which we thought before that the inner halo and outer halo was distributed evenly in spherical distribution, but the streams are not that. The distribution is like a thin line in the positions. We call it then streams or clouds or overdensities. So from the formation should be maybe from the tidally disrupted small galaxies or globular clusters as they accreted into the Milky Way. So then Ibata and Majewski found that there's a Sagittarius stream, and also Newberg in 2002 found the monoceros streams, and also there's also clouds or overdensity of patches of stars with certain magnitude in the Virgo overdensity, and also Hercules Aquila. The mechanism of this could be simplified, but because the galaxy is rotating, our galaxy, and the dwarf galaxy was circling also the Milky Way, and we have also what we call it as dynamical frictions. Dynamical friction, if this is a dwarf galaxy, this is the potential of a galaxy or stars of our galaxy. If they pass our galaxy, and the stars here in behind galaxy will make some, like we call it a clump. So there's a force direction to the behind different with the angle of velocity here, from the direction of velocity. So since the dwarf galaxy is not a rigid body but belong to the star, so their stars were trailing like this. They, because of this gravitation, and also in this part also making some over density, so it starts with kind of like this. So we have tidal tails of germ like this. This is, if the direction is this, so there's a front tail, it's the tidal tail. This is our pictures of our galaxy. There's this, and there's also like a Sagittarius stream or Sigu dwarf galaxy. There's also Ursa Major dwarf galaxy, and also the Sagittarius stream here, dwarf galaxies, and they merging with our galaxy. This is Sagittarius and Ursa Major, and all is inside the dark matter halo. So these artist conceptions about the stream, tidal streams from the dwarf galaxy merging with the Milky Way. This is also a Sagittarius dwarf from the Gaia data simulations, from this Gaia data model, and this is about 8 billion years ago and merged with about 5 billion years ago. So they assume that the collision with the galactic disk about 5 billion years ago could be trigger the formation of stars in the galactic disk, including our suns about 5 billion years ago. And maybe because if the Sagittarius dwarf galaxy did not merge with our galaxy, maybe our sun will not been born 5 billion years ago. This is they assume that from the backward simulations. This I will show you this simulation of disky Sagittarius dwarf galaxy from my students. Here is the galaxy, a dwarf Sagittarius dwarf galaxy. We model with the disky distribution with the halo, dark matter halo, and after a few billion years, they will see that there's a tidal tails here. So let me again. This is the red one is a dark matter particles. Now we can see this tidal tails in the including in this. We can see these tidal tails from observation near the sun, and we can compare the distribution of these streams, or and we can measure if our when it's really accurate or not. In other galaxy also with a good technique in observation, we can determine these dark patches from merging satellite galaxies in other spiral galaxies like this. So actually, so it we can conclude that the lambda cold dark matter paradigm in cosmology, when we galactic the dark matter clump into other and accreting the gas and create stars, the first generation of stars, and then all this dwarf galaxy merge become a big galaxy. So we can also, so the formation of galaxy is still ongoing, not stopped few billion years ago, but still ongoing. This is a simulation also from this galaxy. So we can see the satellite. I will fast again. This satellite, the smaller dark matter dominated system in our local group, nearby system, and also there's other M31 Andromeda galaxy. Now we currently about 20s, more than 20s satellite galaxies. Most of them found in the SDSS survey. First, we have our nearby satellite is a large Magellanic Cloud and small Magellanic Clouds. And also there are also the ultra-faint dwarf galaxy here. It's a dark matter-dominated stellar system with very low mass, but high mass-to-light ratio, about 100 to 1,000 mass-to-light ratio. It's difficult to detect, but with a large telescope and good observations, we can measure this, find this ultra-faint dwarf galaxy. And why are they important? Because we have some missing satellite problems. From simulations, cosmological simulations, we predict many more, about 10 or 100 dwarf galaxies circling the galaxies, a simulated galaxy. So now the SDSS discovery found, not only tens of 20 dwarf galaxies, so it should be many others, but we can only detect only about 10 or 20 dwarf satellites. So maybe it's the problem with better understanding of the galaxy formation and small scale, and we can solve this problem because they are building blocks of our galactic halo. But others say that maybe the problem also with the lambda cold dark matter paradigm, because some other some challenge with the modified Newtonian dynamic or other who challenge the dark matter model. This is a same amount of dark matter. This is a W1, Leo 2, and Fornax. The luminosity is 10 million lumens of the sun. It is 1,000 lumens of the sun. It is very small, few stars here. But the mass, the total mass is almost the same. It's about 10 million solar mass. So you can imagine that the dark matter is, dominate in this ultra-faint dwarf galaxy. So it's important to us to measure every satellite galaxy we found. And this, we model the local dark matter, global dark matter halo here. And with we can compare in the, maybe you can later in the cosmological side about the density of dark matter from simulations. And this is a merger that led this recent paper from Gaia data. Using Gaia, they call it Gaia Enceladus. This is the recent major merger from the galactic satellite and form the inner stellar halo and thick disk. And other team found, they call it Gaia sources, because from distribution it's like you cannot see it. There's another plot. It's just like a sausage distributions here. The same. So the more accurate distance and velocity, we can measure the stellar halo with more complete, and to find any merger process, and also the dynamic process of formation of our galaxy. This all galaxy in the local groups distribution is all dominated by the dwarf galaxy, globular cluster, ultra-faint dwarf galaxy. Large galaxy only, we have only two, Milky Way and M31, and also elliptical bouts, and this is an irregular galaxy. This is a list of bright satellites galaxy near the Milky Way, and this is mass to light ratio correct with the absolute magnitude of the stars in the dwarf spheroidal galaxies. This is Fornax and Leo, and more faint dwarf galaxy has a higher large mass to light ratio until more near 1,000 mass to light ratio. Okay, I will stop here. This is structure branch from our current knowledge about formations of the galaxy with the lambda cold dark matter. With start, they clump, the dark matter clump, and then merging into cosmological merger tree and become a larger one. The larger one is a galaxy nowadays, galaxy. So maybe with the formation, the merger is still ongoing. So we need to understand more. There's because many discrepancy between the model and the observational data. For example, that the missing satellite problems. So the idea is we have to change the idea. It is dark matter point of view is still right, or it can be falsified by the other paradigm of knowledge, our knowledge about the cosmological, about our cosmological knowledge or universe modeling. You need also the model in simulate the galaxy universe with the more complex interaction. Okay, Ms. Luki, I will give back to you.
Okay, thank you very much, Dr. Ikbal Arifyanto. It's very exciting presentation. So we have some question here, and I will read it for you. Okay?
Yes, yes.
Or if you want, we can ask the participant to, since we have enough.
Yes, please.
We can ask the participant to say by themselves. So okay. I will call Thomas Nabil Taufik from Egypt. Are you there?
Yes, I'm here.
Okay. Yeah. Can you unmute your microphone and also show yourself?
Yes,
please.
Okay, yes, please.
Yes, please.
Okay, I wanted to ask when Dr. Ikbal talked about the various relations of the Milky Way potential, I wanted to ask about the underlying assumptions about under such equations, and to what extent are they approximate?
The potential distributions, right?
Yes, in the very different regions of the galaxy.
Okay. Different region. Yes. First, we measure from the stellar distributions. First, we measure the stellar distribution from light distribution, and let me share this. Okay, if we know the distributions, for example, bulbs, and we measure the density, surface brightness, this, for example, R, and surface brightness in magnitude, so we can find these plots. So we can model using this, for example, R related as a function. For example, it's R over 3.2 or 0.3 R per R0, for example, and because it's the unit is luminosity per parsec square, we can change to the mass density. If we know the mass to light ratio, so we can with the density. This is so in different also for this part, so we can also measure this relations. For example, for bulbs like this, and for this, it's a more exponential relations. So also in different parts, so in different part of galaxy or in other galaxy or in the Milky Way, we can using this. And if we know the density, there's the I forgot the relation, but this called the potential density pair. You can check in the book Galactic Dynamics. Bini Trimain. This is a potential density pair. So if we know the density, surface brightness, we can change it with assume mass to light ratio. We know the density, we can change to potential, like a Poisson in the Poisson, Poisson rule. But if we assume also, if we know the potential, okay, galaxy is like a disk-like structure, so we know we create the potential, and also we can change to the density. It depends. You can back and forth. I hope this answers your questions.
Okay, thank you very much,
Yeah.
Dr. Ikbal.
Yes.
So now I will call Tan Wenshen from Malaysia. Are you there?
Yes, I'm here.
Okay, can you tell your question to Dr. Ikbal?
Yes. Doctor, can you go to page 12?
Page 12. Okay.
Yes, of the slide.
Okay. Wait. Oh, sorry. This one?
Wait, I'm not just maybe one slide earlier, 11.
This one?
Yes.
Yeah.
I want to ask. In the left hand side is the B square R is observation.
Okay.
In the right hand side also got VH1 is also from H1 observation.
Yes.
What is these two difference?
Oh, okay.
The H1 observation.
This. Okay. From I-band photometry, it's from the stars. If you know the distribution, because dominate usually for I-band photometry, it's an near infrared. You can measure a star, maybe low mass stars or giant stars with certain distance. So you can measure also the velocity of star. But the hydrogen one is from interstellar medium, from interstellar gas. It's different way, but okay. Observation, and this is model. Okay. What you mean is for observation and model, right?
Yes. And the VH1 also from the H1 observation. You write in the second
Okay.
sentence.
Yes. Okay. Yeah. Okay. I okay. So wait, this one. Okay. For example, this one is from hydrogen neutral. Sorry. Rotation curve from this data is from H1 hydrogen neutral. And okay, this is halo and this mass from I-band photometry and different choice and dark matter halo. This is okay. Oh, okay. I think I well, okay. Observations and model. Now, yeah, this is not from H1 observation like rotation curve, but it's from contribution of the gas. Contribution of gas. This is not model. Okay. My failure. Sorry.
No. Sorry. Then may I know which gas is that?
Sorry.
Which gas is that? Is that it consists of H1 as well? The gas.
Yes. It's H1 and molecular cloud, because dominant gas is about 80-90% is in hydrogen.
So what is the difference of for the left hand side, the total one? The total one and the H1 observation. What is the difference? This one and the total one.
Okay. I should delete this model. Yeah. This is from halo. This is from gas into the disk. What you mean? This is a gas only, contribution of gas only, and this is from gas, and this is from stars.
My question is the total one, the left
This
one.
one?
Yeah. How
Okay.
you obtain this from? Is it from observation?
Yes, yes. Observation. Like, okay, sorry. This one. This is from observation. Okay, there's two. First, we can measure the rotation curve from interstellar gas. We measure only the velocity of the gas. Usually using tangent point method, this is less than 8 kiloparsec. We can also measure from the stars or clusters outside the solar circle. Here, from here, this. But from the velocity distributions, it's from this we want to model this part contribution from stars and contribution from gas also, how mass density. Usually the gas essentially assumes flat as a very thin disk with a very low, maybe about 100 parsec scale height, and we assume the corona. So we from the data is here, and this is the model. This is information from gas distributions. You can you know, yeah, actually it's right. It's a model distribution of a gas with the density of gas, and this is density of the stars. So we found this plot like this. I hope this answers you.
I think so. Thank you.
Okay, you can contact me again if it's not.
Okay, thank you.
Yeah, welcome.
Thank you, Dr. Ikbal, and thank you, Tan. So now I will call the next. Okay, the next question is from Dio Danarianto. Are you there, Dio? Can you turn on
I'm
your?
here.
Okay.
Can you hear me?
Yes.
Yeah.
Yeah.
My question is simple. Is there any way to probe the dark matter without measuring the kinematics of stars or star or other object? It's like a direct observation, maybe.
Yes, direct observation. We'll hear some of the talks later in this summer school, because some professor also from Korea that will be invited lectures will talk about the direct measurement of the dark matter. But in the scale of the galaxy scale or in the local scales, the dark matters are related to the gravitation. So how to measure, the problem is how to measure the gravitational effect from dark matter to the stars. So we measure the kinematics, unit position and velocity, because gravitation works like that. That's Leo. I hope you answered.
Yeah, thank you.
Yeah.
Okay. So the next question is from Vanesha Jihan. Are you there, Vanesha?
Yes, I'm here.
Okay, please.
Yes.
I have a question that so far we talk about Milky Way, but can this method apply to the other galaxies?
Yes, of course. The rotation curve method you can apply to other galaxies. But it is, as I explained before, we need information about the mass, surface brightness of the galaxies, and we model with our knowledge about mass to light ratio, and then we determine the mass density, and then we determine the potentials, and also we can measure the rotation curve contribution of the halo.
So from this method we can apply to the other galaxy, but still need the raw total, the density, total density, right?
Yes, you can measure the total density. Yes, from the rotation curve. Yes. We will give the workshop in this summer school. One of them is how to measure the rotation curve and measure the dark matter in the other galaxies. Okay.
Okay, thank you.
You're welcome.
Thank you, Vanisha. So the next question is from Muhammad Hassan Zaki bin Yusuf from Malaysia. Are you there?
Hello, can you hear me?
Yes,
Okay,
yes.
please.
Okay, let me see again my question. Yeah, I was asking about the same equation that you have been shown before. Because I see the equation a lot, and in one of my local presentation,
Yeah.
somehow the question arises that how do you prove that it look like what do you call Pythagoras in a simple way, but you got another component with a square symbol, right? And then how do you prove
Square
that?
symbol.
Yeah, the whole equation. How do you prove that it's true, that we can use it to prove the total velocity component of the galaxy is the total of all that included in the equation?
Okay. Okay. First you have rotational. First you have the rotational function is equal to Gm is a function of r. It's like this, right?
Yeah.
If you square is G over R. So mass equals to V rho square, right? So the total mass is the mass of this, mass of bulbs, and mass of halo. Since it's related to the velocity, so it's a V total equal to V this, V bulbs plus V halo. This is the combination. This is what you mean?
Yeah, and so you can just simply
Yes.
like replace m and v, so you got the equation.
Yeah. Yes.
Okay.
Because it's the same distance. You measure in the same with R, say 10 kiloparsec. This is also 10 kiloparsec, 10 kiloparsec. The plot is the same, right?
Yeah.
This is contribution of bulbs, this, and this is the halo. So you measure from this point. So you can contribution mass and between this.
Can I add one more? Is there any condition or specification that we have to maintain while using this equation, or is really flexible?
What do you mean with maintain?
I mean, like, is there like something like we use it on different galaxy, and then also we use it on different model like Burkett or NFW and then?
Oh, it's the same. We can choose the same. You can change the this velocity distributions because it's related to the mass. Mass related to then to the potentials. Then so you have to define different potential or density, like that.
Okay, I see.
Yes.
Okay, thank you.
Yeah, you're welcome.
Okay, thank you. So next, I will call Ankita Wakna from India. Are you there, Ankita?
Yeah. Hello.
Yeah, please.
Okay.
Yes, please.
Yeah. Hello. So my question is, how will the collision of the Andromeda galaxy with the Milky Way affect the solar system?
Effect of the Andromeda galaxy with the solar system.
Yeah, with the Milky Way. Like, how will the collision of the Andromeda galaxy with the Milky Way affect the solar system?
Yeah.
Okay. I think there is some simulations because the Andromeda has a blue shift, it's a blue shift, and our Milky Way so in the direct almost in direct collision, but in a few million years. But first you have to know that maybe I don't explain because the density of stars in the Milky Way is very low. It's about less than you can say 1 star per parsec cubic, something like that. It's very low density. So in the galaxy, in the galactic disk, with very many stars, and so if the Milky Way and Andromeda galaxy collide in direction, there's no chance. I think I can ensure that no star will be head-to-head collision like that, because there's very small density. But it can be triggered the gas. The gas can be different way. It can be trigger the star forming region. But I think our solar system is still safe. We are still there. Yeah. Okay.
Okay. Thank you.
Yeah. Welcome.
Okay, thank you. And the next question, it is the last, I think, is from Mark Ivan Ugalino from Philippines. Are you there?
Yes, I'm here.
Okay, please.
Good afternoon. Thank you very much for that talk.
Yes.
I just want to ask what the current standing of modified Newtonian dynamics is against our current dark matter models, that is in describing the dynamics of Milky Way galaxy. And if we are successful in detecting dark matter directly, will it directly vanquish the existing MON theories?
Okay, thank you. Very good question. But let me, postpone. You can postpone this question until maybe until almost the end of the
Wednesday. I think Wednesday we will talk about that.
Yeah, and also there's our guest Federico Lelli. And you can check the he will talk about the MON. If you know, if you so there's in YouTube, there's a debate between the dark matter group and then MON group, and you know that Federico Lilly is part in the MON group, so you can ask him later about condition.
Okay, thank you very much.
Okay, you're welcome. Okay.
Okay, thank you very much, Dr. Ikbal, and thank you very much, everyone. You've been a really wonderful participant, very active, good job. Now, before ending this meeting, we will have photo session. So now, everyone, let's turn on your video, and also you can also turn on your mic to give applause to Dr. Ikbal Arifyanto.
Thank you.
Thank you.
Okay, so please turn on your video. And Dr. Anton, are you there? Will you help us to take a picture?
Okay. Okay, please give us the best smile. Okay, keep smile. Okay, 1, 2, 3. Okay, I guess it's only one. Okay, okay, for the second one. Okay, let us check. Wait a minute. Okay. Okay, 1, 2, 3. Okay, done. Thanks, everyone.
Thank you. So good job, everyone.
Thank you.
See you again in the next tomorrow. Yeah, we see you again tomorrow. So thank you very much again, everyone. So I will end this meeting and see you tomorrow.